Ever wondered why AI models sometimes act like they're learning between tests? Or why one study calls a model a genius while another deems it average? The truth is, how we test AI is as critical as the model itself. Today, we're diving into a groundbreaking study that's reshaping how we evaluate these systems, and why it matters for researchers, developers, and users alike. Let's start with a fundamental concept: test repetition. Imagine grading a student. If you ask them the same question once, their answer might hinge on luck. But if you test them 32 times, their true ability emerges. In our experiments, we found that performance stabilizes when models are tested 32 times, with fluctuations under 1%. But here's the twist: some models like DeepSeek 1 QN1, 5B are hypersensitive. Their results swing wildly unless tested extensively. Meanwhile, models trained on larger datasets, like GPQA Diamond, show remarkable consistency. It's like comparing a flickering flashlight to a steady lamp. Bigger data equals more reliable output. But here's where it gets wild: the random seed. Think of it as a secret ingredient in a recipe. If you don't specify it, the system picks one at random. And that tiny variable can wreck your results. In one test, we kept the seed constant but ran the model 16 times. For smaller models, some seeds turned them into problem-solving wizards, while others left them floundering. It's like flipping a coin. Without knowing the rules, you can't trust the outcome. That's why we now always document the seed. Transparency isn't just best practice, it's the new gold standard. Now let's unpack datasets, the questions models are tested on. Did you know there are multiple versions of the same dataset? One might include images, another might omit them. We tested this and found models scored up to 3.9% higher when they could see the full picture. It's like solving a math problem with or without a diagram. Sometimes visual cues make all the difference. This means if you're comparing models, you must ensure they're tackling identical challenges. What about task instructions? We tested models with instructions placed before or after questions. The results: some models adapted seamlessly, while others faltered. It's a reminder that even subtle changes in setup can skew outcomes. Let's break down the data. These tables reveal how models perform across tasks. Each model was tested 16 times with the same seed, like a recipe with consistent ingredients, to measure reliability. The averages in the last three columns show their typical performance. Take DeepSeek 1 QN32B, for example. On AIME24, a math benchmark, it scores 70-75%, while the 1.5B version hovers at 25-35%. But here's the kicker: bigger isn't always better. The 7B model outperforms larger ones on GPQA Diamond, a dataset testing creativity and reasoning. Why? Because different datasets prioritize different skills. AIME might focus on precision, while GPQA Diamond rewards adaptability. And look at the fluctuation metrics. They measure performance variability between runs. Lower numbers equals more stability. OpenRSGRPO has near zero fluctuation, making it a reliability workhorse. So what's the takeaway? These experiments aren't just about raw power, they're about understanding how models adapt. Whether it's math, logic, or creativity, the best model depends on the task. This research isn't just academic. It's reshaping how we build, test, and trust AI. Because the real story isn't in the numbers alone, it's in what they reveal about how machines learn. Stay tuned as we explore how these findings will define the next era of AI.